Hello.
Good evening, sir.
Yeah, good evening. Welcome on board.
Yes, sir.
We are good to go. We started this topic last time, interaction of irrigation with matter. We're going to conclude it today. We have looked at Raleigh scattering, we've looked at Compton scattering. Today we want to look at photoelectric emission. Photoelectric emission and of course, production for completeness sake. I've looked at Raleigh, now Compton. Let's continue with photoelectric emission. Photoelectric.
Hello, sir.
Hello. Can you hear me?
I can hear you.
Okay.
Dr. Yara, can you hear me, sir?
Yeah, I can hear you.
Yeah, Dr. Yara asked that she send me a link. Should I go ahead?
Of course.
Ayirara, you know the person?
Yeah.
Okay, no problem. I will send him
Okay,
the
let's
link
go.
now.
Photoelectric emission. In Compton scattering, we had the electron, the photon, interacting with a loosely bound electron. Of course, it's about essentially zero energy. The atom's electron, their binding energy are very, very close to zero. So it could be easily detached with any photon that has appreciable energy. But for photoelectric emission, the interaction is mainly with the K shell. Of course, at times L, and very rare cases you have N, and so on and so forth. For photoelectric emission to take place, you have interaction with a tightly bound inner electrons, such that the electron will be ejected. Have a photoelectron, and so many things now begin to happen. So many things. You have electrons from the next shell filling the vacancy that has been produced by the injection of this electron, and so on and so forth. At the end of the day, we are going to have a cascade of electrons. You have so many shells, and you have 2, 3, 4 shells. You have electron filling here. A vacancy will be created here, M shell, and so on and so forth. So something continues until the atom now becomes neutral again. So we have in photoelectric emission, the photon energy is completely absorbed by the electron. It's completely absorbed by this. It is different from what we had in Compton, in the sense that the electron absorbs a part of the energy, and the remainder of the energy is given to the photon, another photon with a different wavelength, and of course a frequency that continues on the different routes of path. But for this, we have the total energy taken over by the electron, and we now have so many things happening there, cascade of electron from one shell to the other, and so on and so forth, with the emission of energy, characteristic energy, and so on and so forth. Like we have treated before, the um, coming back to stability of this atom can be in form of a photoelectric emission. Sorry, can be in form of a characteristic emission, characteristic X-ray, or electron. Okay. Okay, electron. So essentially, two things some things we need to note between Compton scattering, and photoelectric emission. In Compton scattering, the photon's energy is not totally absorbed by the electron. Just a part of it is absorbed by the electron, and the rest is taken over by another photon that appears with a lower energy than this. And of course, the energy is just shared between the photon, the new photon, and then the Compton electron ejected. That is one. Another difference is this: in photoelectric emission, the interaction between the photon and the electron is that the electron is are those, the electrons we are talking about are those in the innermost shell, most especially the K shell. So we do have some photoelectric emission that occurs with other shells, but the most important one, the most common ones are the ones that have K shells being K shell electron being ejected from the atom. And again, the probability of photoelectric emission occurring depends at times depends on so many values. So many factors, both on Z of the material and the proton number, the electron, the photon energy, among other things. Two major ones. When it comes in terms of energy, in terms of Z, photoelectric emission coefficient is directly proportional to this. Photoelectric emission coefficient is directly proportional to Z to the power 3. It's also directly proportional, inversely proportional to the energy raised to the power 3. So combining these two equations, we have it to be indirectly proportional to Z 3 over E raised to the power 3. You can see this is greatly affected by the Z of the material, and of course the energy of the photon. It is not the same thing with Compton scattering, in which it is not so dependent on Z. It's not so dependent on Z. Just sparingly depends on Compton. Of course, it's also indirectly dependent on energy, which is which has this value, which is not squared or equal or anything. It doesn't have so much effect of energy dependence like we have in E. A little change in energy causes so much change in photoelectric emission, while the same amount of energy change wouldn't cause so much for a Compton. Those are two. And again, we have that photoelectric emission, since we don't have Compton, we don't have another photon produced. We don't have a photon that is scattered. This is essentially of importance in radiology, in diagnostic and imaging. This is the major contributing factor to contrast. This one doesn't contribute so much to contrast. It actually degrades a lot, except if the scattering photon is in the same direction with the incoming photon. That is when it contributes to some amount of contrast. But if it now begins to deviate at an angle, then we don't have, it wouldn't be responsible for a contrast. Let me share a screen with you. I hope you can see the screen.
Yes, sir.
Okay, you see, we have an atom. Look at the atom. Look at the array of an electron. These are these electrons, or rather, this diagram has just been drawn here, just as illustration. It doesn't depict a true atom anyway. So we have electrons here, incoming photon that's interacting with this electron, being given off, and after the electron was given off, we have a vacancy created here. The vacancy was replaced. The vacancy was occupied by another electron falling from this L shell to this K. From there, a vacancy here was created here. We now have a transition from this shell to this. Likewise, from here to here to do the vacant to fill up the vacancy. So there's something continuous depending on the number of shells we have. And you can see so many characteristic X-rays given up. For the first one here, the difference in the binding energy of this one and this one will give us 28 kiloelectron volt, 33 minus 5. And the difference between this shell and the characteristic energy of X-ray that will be given off here is just the difference between the binding energy of this shell and the binding energy of this shell, which is 4 kiloelectron volt. Likewise here, this one is just essentially zero. It's not as if it has no energy, but the energy is close to zero. 0, 1 minus 0. It's going to give us the characteristic X-ray for this transition from this shell to this other shell. So this is just the diagram depicting photoelectric emission. I said it is indirectly proportional to energy, likewise pumping. Very, very, very direct relationship with both Z and E. For both characteristic, for both Compton scattering and the photoelectric emission, we normally have the energy of Compton.
Hello, sir. Hello, sir.
Hello, I can hear you.
We can't see the screen, sir.
Oh, so sorry. I didn't stop the share. Okay. I wanted to talk about absorption and energy. I said both for Compton. The Compton graph is somewhat like this. Whereas the photoelectric emission looks more like a straight line. Because it has a very, very linear relationship or direct relationship with energy. Photoelectric emission over energy. And see, has the drop is the graph has a very, very sharp gradient. I want to calculate the gradient sharp compared to the gradient of like this. We could see that for photoelectric emission, This is the energy. Right? This is the percentage of interaction. Percentage of interaction for protein, battery, and this is for the electric emission. The two of them, at some point in time, you have an increase in energy. I mean, increase in protein and scattering as the energy increases. But after some point in time, it begins to drop drastically. I mean, it begins to drop, not drastically. But for this, something, the drop is very, very drastic with an increase in energy. Energy emission continues to decrease. So we have this line is not so straightforward. There's a point in time in which we have a spike. Which will have a spike. It occurs at what we call the KH. KH. There's a sudden increase in the probability of a photoelectric interaction. Photoelectric interaction when the photon's energy reaches the KH of the atom. The KH of the atom is essentially the energy, the binding energy of the K shell. The binding energy, that's the energy holding this electron in its orbit. So when the photon energy continues to, as you are decreasing the energy, as you are increasing the energy, the probability of photoelectric emission continues to decrease. But at a particular point in time, when the energy of the photon just reaches the binding energy of the K shell, K shell electron, you now have a spike in the photoelectric emission coefficient. It now goes up, then after some time it continues to go down again. If you have you can also have an LH, so on and so forth. You have so on. So this only happens with photoelectric emission. This phenomenon, this feature is made use of in selecting filters, especially when it comes to mammography. Filters are so selected so that you have so much portion of characteristic X-ray than a bremsstrahlon, because with enough characteristic X-ray, you could fine-tune the spectrum, the X-ray spectrum, to be somewhat manageable. So these are some of the features of photoelectric emission. The presence of absorption edge. So for pair production, we just need to know about pair production, just for completeness and sake. The threshold for production of for pair production is 1.02 mega electron volt. What is pair production? Pair production is essentially when an incoming photon interacts with the nuclear field or the Coulombic nuclear field of the nucleus, and suddenly the deceleration will bring about the conversion of this energy to matter. Remember, E equals mc squared. Matter can be converted to energy. Energy can also be converted to matter. So when this photon is traveling, if it doesn't interact with the orbital electron, it can enter into the nuclear field of this material, of this atom. And in doing that, the deceleration will bring about, this interaction will bring about a production of a pair of oppositely charged material, beta, positron, and electron. As they are produced, they will not travel in different directions. So this is their point of so this is the point of production. They will travel a different direction, 180 degrees, about 180 degrees. Electron go this way, while this position that way. So we come to know more about this in the first production. I mean in first scanner. So this is essential. And then the two of them we have, of course, the rest mass energy of an electron is 0.511 mega electron volts. Equally this 0.511 mega electron volts. If you don't have, if the energy is not up to 1.02 mega electron volt, we can never have a fair production because we cannot have an electron whose mass, rest mass is less than this. It's not possible. Then if you have a photon whose energy is greater than 1.02 mega electron volt, after the production of the pair, the positron and then the electron, the energy, the remaining energy will now be given to these two in form of kinetic energy, which they will now use in traversing matter, traveling some distance before they now interact and lose their energy locally. So that is that about interaction of X-rays and the photons with matter. Of course, we have some other interactions which are not very important, which are not important in this diagnostic energy range, like triplet production and photon integration. They are not very important, but we could read them of those for knowledge sake. So now look at, now go over to attenuation of attenuation. Photon. And the photon, of course, has a gamma ray, and X-ray. When photon traverses matter, of course, it loses energy. And the energy loss is as a result of the interaction of the photon with matter. They lose energy by both absorption and then scattering. They lose energy by scattering and absorption. The two major ways, of course, as energy, as photon continues to traverse the matter, it begins to undergo interaction with so many things, electron, the nuclear material, and so on and so forth. The energy continues to reduce. Absorption, the material, of course, absorb some of this energy, and as a result, we have lesser energy. So we want to look at some of the important terms we are going to be looking at. I mean, we will encounter under attenuation. The first among the list is a linear attenuation coefficient. Linear. Attenuation coefficient. At times, you might want to look at, excuse me, this. At times, you might want to look at the linear attenuation of a photon beam. That is how energy is reduced in a linear fashion. We might have n particles or n photons are moving inside the matter. But after some time, we have n photons removed by means of scattering and absorption. We want to look at how it relates to the thickness of that material. So if you have N, this is a ratio, a fraction. And this fraction, which tells us the amount of X-rays or gamma ray photons removed, is that directly proportional to the thickness of the material. The more the thickness of the material, the more the number of photons that will be removed. For example, you have 1,000 photons with 1 millimeter thickness of maybe lead or aluminum. If we now increase the thickness to 2 millimeter, the number of photons that will be removed will increase, assuming this is a linear. Assuming this is a linear, I'm going to explain that further. We now have 500 photons after we introduce a thickness of 2 millimeter. So if we introduce a constant of a proportionality, n over n that is proportional to. So this constant of the proportionality is what we know as a linear attenuation coefficient. Mu. This is a linear attenuation coefficient. You can have this written as n. So this is the thickness of the material involved. This is the linear attenuation coefficient, and this is the initial number of photons, whereas this is the number of photons that have been removed from the X-ray or gamma ray. This is a very straightforward. At times, it is not as straightforward as this. This equation is only valid when the when delta S is very small. When we are talking of a material whose thickness is very small, very small. But when the thickness becomes thick, when the thickness becomes large, this equation no longer holds. So we need to introduce another equation that will take care of this, of everything. This is just a myopic nature, a myopic look at the concept of the linear attenuation coefficient. But if you want to have a generalized view of linear attenuation coefficient, we need to introduce a calculus. But I don't want to bother you with that, just for us to know the equation. But if we've done radioactivity and so on and so forth, the equation shouldn't surprise us so much. We call it n equal to epsilon. So let me still use my data is the thickness. Or let me just say thickness x of completion. Now this one we can put x here in as much as we know what we are talking about. X is the thickness of the material. So when we have thickness of any dimension, this equation is, of course, what we use. And for we have to be careful here. And maybe perhaps I shouldn't even use this n so that it doesn't confuse us with this. Let me say okay. I can still use n. Just for us to be sure to know that let me use n naught here. Let me use n naught here so that we don't mistake this n for this n here. This n is the initial number of photons we are looking at. Initial number of photons we are looking at. Then This N here is the number of transmitted photons. It's different from here. This one is the number of attenuated photons. That is the number of photons that have been removed. Whereas this N in this equation is the number of photons that have been transmitted. That is, you have a thickness, a particular thickness, you have a photon. Maybe you have 3, 4, or 5. At the end of the day, you have just about 2 photons passing through. So this is the N here. This is the N naught. Whereas the 3 that have been absorbed here, 1, 2, 3, the 3 photons that have been absorbed by this material is N. So we should just take note of that, that we don't get confused when solving problems. This linear attenuation coefficient has a direct bearing on the density of the material. And the more the density of the material, the more attenuation that material offers. For example, you have a very, very dense material. For a material that is dense, it offers much more resistance to passage of photon. You can compare a material whose maybe internal structure like this. As in the separation of the particles. And compare it to one whose internal structure, the separation of the atom. This one is denser than this. And as such, this one will allow much more photons to pass through, whereas this one will block so many photons from passing through. So in terms of density, the more the density of the material, of a particular material now, the more the attenuation that material is going to present to the photons passing. So density is very, very key. It's a factor that determines the rate at which a photon is going to be attenuated. Having said that, we have the total linear attenuation, because during any event of photon traveling, all the processes, all the interactions we have mentioned so far, all of them happen, except for pair production. When the range has not reached 1.02, then we will be limited to the 473 attenuation. That is Rayleigh scattering, scattering, and the pair production. But if it's more than 1.02 mega electron volt, then we are talking about the 4. So total, in totality, the total linear attenuation coefficient is just simple, a contribution by Rayleigh scattering, contribution by Compton scattering, contribution plus photometric emission, and then contribution by reduction. So just a summation of all these interactions will give us the linear attenuation coefficient. Linear attenuation coefficient is very, very important. We want to look at the energy, or we want to look at the energy. Yes, the energy we need in for a particular diagnostic procedure. Let's say you want to image a particular portion of the body. We might want to look at the linear attenuation graph and see the best energy that will give us the best contrast. I mean the energy, or so let me say the mean energy that will give us the best contrast. Also, if you look at the graph, something this production from 1.02 starts and then continues to increase. If you look at this, we want to look at the best energy, the energy that will give us the greatest contrast. Because we continue to increase, you see the difference here. But at this point, we might not have any contrast or so. because the contribution of this and this one will cause so much scatter, whereas this one whose this catalytic emission, which is responsible for the main contrast, will be counterbalanced by the scattering that's contributed by the Compton effect. So we want to look if it's a linear attenuation coefficient, you can get the energy, the photon energy. This is energy. The photon energy that will give us at the best contrast. So if we don't want to look at linear attenuation coefficient, we don't want to look at the attenuation by means of the relationship of or length, linear relationship. And I want to consider another type of attenuation or mass attenuation coefficient. In mass attenuation coefficient, we don't want to bother ourselves with the density. It is what we want to look at when we want to look at the rate at which energy is removed from the material. If that is our concern, then we don't bother ourselves with linear attenuation coefficient and look at mass attenuation coefficient. And mass attenuation coefficient is just derived by multiplying or dividing the linear attenuation coefficient by a unit density. That is, if you have linear attenuation coefficient divided by rho, that gives us a straight up mass attenuation coefficient. I don't want us to dwell more on this. Just get a linear attenuation coefficient divided by the density of the material. We have gotten a new term, which is just the mass attenuation coefficient. We have not, of course, the unit of linear attenuation coefficient is usually in per centimeter, because we are looking at a number of blah 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 per, as we have n over n, that's proportional to divided by s. So we have n is equal to the whole of this is a number divided by n over n is a number divided by x. So that gives us 1 over centimeter, that's per centimeter. So this is the unit of linear attenuation coefficient per centimeter. It depends, and at times you can also be given a millimeter, just for us to know the units are given when I doing calculation, and we don't make mistake. You can begin to divide a centimeter by a millimeter. So we either have the two units are the same in centimeter, meter, or even decimeter and so on and so forth. Just for us to have a uniformity when we are doing a calculation. So this is just the little and that. Let's go to some other very, very important points we need to know. Definition. I want to look at the half value layer. This is one of the most important AGL. Half value layer. At times we want to look at the energy of a beam. The energy of a beam, is it 50 kiloelectron volt, 20 kiloelectron volt, and so on and so forth. In order to do that, half value layer can give us a rough estimate of the energy of the beam. A beam that has a high HVL is more energetic than the one that has a low HVL. In fact, during acceptance testing, when a machine comes, the half value layer test, HVL test, is one of the most important tests, because if you don't do that, the machine, the X-ray machine, the CT or whatever, may not be operating optimally. You might just have some little small doses. I mean, small X-rays which don't contribute to contrast. We don't contribute to, of course, event imaging. What they just do is just to be deposited inside the patient's body. And at the end of the day, the patient has more dose than he or she should have, which wouldn't add anything to image and quality. So HBL test is an important test we need to do. High value layer is just the amount of thickness of the material that will reduce the intensity by 1/2. Let's say you have 100 photon, you have 100 X-ray traversing a particular length of tissue, particular thickness of tissue. If that tissue thickness reduces the number of photons traveling, moving inside it by 1/2, then we are talking about that thickness of material is the HBL. That is, you have a photon, you have so many photons traversing a particular material, is formed, and then at the end of the day, you have two remaining. This material, this thickness of material is HBL. That's the HBL of that particular beam. If this is aluminium and this is 2 millimeter, it means the HBL of this aluminium for that particular energy is 2 millimeter, and so on and so forth. If we are looking at a lead, of course, we know that it has to be smaller, maybe around maybe 0.4 millimeter to be able to effect this type of to reduce this by 1/2. I'm just comparing different material. But HBL is essentially the thickness of the material that will reduce the number of photons, number of of course, gamma ray or X-ray by 1/2. I can still use that equation to do the calculation. If we have n equal n naught for HBL, it's n over n naught plus e minus n over n naught should just be half. This ratio should be half, 1/2. If you have 50 over 100, 1/2, 20 over 40, 1/2. Initially, we are starting with 60, but at the end of the day, we had 30, 1/2. So if we minus this value is now a HBL. HBL. This thickness of material is now a HBL. So at the end of the day, I could do some little. If we find the natural logarithm of this side and this side, we are going to arrive at this what's it called? 0.693 minus 7. So at the end of the day, we have a HBL equal to 0.693 over linear attenuation coefficient. So this is an important equation we all need to know. So because the HBL of the material is inversely proportional to the linear attenuation coefficient. So the more the linear attenuation coefficient, the lesser the HBL. So HBL is just a measure of how energetic a particular beam is. It tells us about the quality. At times, another term we can use to quantify energy, to talk about energy, is the quality of an X-ray beam, quality of the photon beam, and so on and so forth. So that's that about that. Let's quickly go to effective energy. We are racing against time. Effective energy. In radiology, especially in X-ray modalities, we don't use a mono-energetic beam. Okay, the nuclear medicine, when we use technetium 99, the energy given off by technetium 99 is a mono-energetic. So if you draw the X-ray diagram, the energy diagram is going to just be like this: 143 electron. electron volt for technetium 99. When it's decaying from when technetium 99M undergoes a metastable isomerism to technetium 99, the energy of the proton that will be released is 143 electron volt, single energy. But for X-ray, it is a number of energies from the least energy to the maximum energy. And the maximum energy is the energy of the incoming electron. So we can have so many forms of energy. So the X-ray beam we use is a term polyenergetic. Polyenergetic, that is, it has so many energy. At the end of the day, what we calculate is the effective energy. We want to look at the effective energy of the beam. And the effective energy helps us to characterize, of course, the quality of the beam. It actually gives us the penetration power of the beam. How can the beam penetrate a matter, seal a fallout from HVL? If we have an energy, an X-ray whose effective energy can also use a mean energy, whose effective energy is 70 electron volts, effective energy. Since, and we have another one, maybe 100 electron volt. This one has higher quality than this. So this one will penetrate more than this energy, than this photon or X-ray energy. So the more the KeV, that's why the KeV is the measure is the unit that discriminates between energy. Just for us to know, is going to help us in the next subtopic, which is beam energy. I mean beam hardening. Which the introduction of, in fact, in all the X-ray machines, you normally have filters. You have filters, inherent filters in the material. If these filters are not there, it's going to portend a very, very grave and danger to the patient. Why? Because of the polyenergetic nature of an X-ray, the lower energy X-rays will be absorbed by the body, which wouldn't be used in the formation of the diagnostic image. So at the end of the day, those ones are just useless. So because of that, the lower energetic rays, they have to be removed by use of a special thickness of aluminum and at times copper. So those thicknesses can be 5 millimeter, it can be 1 millimeter, it can be 2 millimeter, depending on the type of machine we are using. With the introduction of those thicknesses, I mean those filters, the energy of the beam becomes higher. It becomes much more. It has a much more quality. So in a sense, we are talking about a beam hardening. We are hardening the beam by introduction of a filter. The more the number of a filter you have, you are introducing, the more energetic the beam becomes. In fact, if you have a particular filter, which you have so many energies of X-ray, you have one this way, you have one very energetic, very energetic. You introduce a particular beam, a particular thickness of material, a particular attenuator. It's going to remove the smaller, the less energetic one and allow the more energetic to pass through. In a sense, you have actually hardened this beam. So that is why, in relating this one to HVL, the second HVL of any material is usually bigger than the first HVL, because at the end of the day, the effective energy of this one is bigger than the effective energy of this one. If you introduce another This one will further reduce the further absorb the less energetic ones, maybe the more energetic. Assuming for this sake, for just explanation sake, let's say we have three types of energy here. The polyenergetic, the photon or X-ray is polyenergetic with three types of energy: 70 keV, have them 50 keV, and have them 60 keV. Maybe this one took off and said, 50 keV, now have the 60 keV and then 70 keV. At the end of the day, introduce this one can just absorb 60 keV, the less energy, and allow 70 keV to go. So at the end of the day, the more the number of filters you introduce, you can see the effective energy of this one is greater than this. The effective energy of this one is greater than this. But if you add the whole of this, the mean energy is going to give you a number lower than this. And of course, this one, the energy is 70. This one, the mean energy is 65, and so on and so forth. So the more the number of HBL, the more the number of attenuators you bring to the first HBL. The more the number of attenuators you bring, let's say the same number of attenuators, let's say 2 millimeter, 2 millimeter. At the end of the day, you are going to have a much more hardened beam. It is different from energetic beam. It has been just 70. What's going to be reduced is the number of particles. Let's say 100 here, to be reduced to around 70 or so on and so forth. So beam hardening is just the phenomenon that involves the effective energy of a beam becoming harder. Should I use that word? When you have an attenuator that continues to decrease, remove and lower energetic beam, X-rays, you now find that at the end of the day, the beam becomes harder. That's a beam hardening for us. Quickly before, I think I'm not going to spend less than more than 15 minutes. We could have some time to go through our quiz. A beam hardening has got to, let me just say, has, before I hardening, we have a particular term in a beam hardening which we call homogeneity factor. Factor coefficient. This has got to do with the first HBL over the second HBL. And of course, the second HBL is always greater than the first HBL. So that is why you always have a particular factor. For most diagnostic range, the HBL, the homogeneity factor is from around 0.4 to around 0.8, 0.75. So, but for energetic beam, the homogeneity coefficient is usually 1 because the first HBL and the second HBL are the same thing. So it will give you 1. So this is usually used in knowing the nature of the polyenergetic beam, whether it has so many energy components or it just have a few energy components. Let's say a beam that has in fact, that is why we normally use a filter, so that the homogeneity coefficient can be increased. So in a mammography, you can have a homogeneity constant of close to around 0.9 because the beam has been so conditioned. The low energetic beam has been so removed that something becomes almost a mono energetic beam. I think that just quickly glance through some radiation units we will be encountering in radiology. Radiation units. Radiation units. So other quantities of this and the measurements. So units and measurements. Radiation units and measurements. The ICRU and ICRP. ICRU and the ICRP. The National Committee on the Radiation Units and Measurements. This one is the International Committee on the Radiation Protection. They meet from time to time to define some units that we use in radiology, radiation, radiology, and radiotherapy. And some of these units, they normally have a revision, like I said, from time to time. So we are going to look at some of these units that we will be encountering in radiology and of course radiotherapy. And one of such units, one of such times is exposure. Exposure is simply the amount of charge that is produced by ionizing electromagnetic radiation per unit mass. You have denoted by symbol X charge level mass. Just want to state it simply that way: charge over mass, Q over M. So you have a particular electromagnetic radiation. I mind those exposure only relates to electromagnetic radiation. It doesn't concern particular radiations. Sometimes you might be asked of that. Exposure has got to do with electromagnetic radiations only. That is ionizing electromagnetic radiation, not particular radiation. Not particular radiation like electrons, positrons, beta, alpha ray. Only for electromagnetic ionizing electromagnetic radiation, that is X-ray and then gamma ray. So if you have a particular amount of X-ray, energetic X-ray passing through matter, of course, is going to cause all those processes we have discussed. At the end of the day, it's going to make the knockoff and 200 electrons within the unit mass. So that is at this equation. Assuming it knocks off, it produces an electron ion pair of it's a charge of 4 coulomb. We are talking about maybe a mass of maybe 2 grams. Then we're going to have 4 coulomb per gram. Essentially, the SI unit for this is coulomb per kilogram. And the SI units, but it has an old unit which we still use up to date, which is given as Röntgen. And the conversion is this: 1 Röntgen, 1 hour is 2.54 times 10 to the power -4 coulomb per kilogram. This should be 2.58. 2.58. So that's the relationship. If you have the unit in a kilogram, in coulomb per kilogram, you can convert to a Röntgen and vice versa. Just rushing. Don't have. So other units which we normally come in contact with, we always, not just normal, absorb those. absorb those. The absorb dose is simply the energy imparted to a particular tissue. Energy imparted to a particular tissue per unit mass. Energy imparted. Energy imparted per unit mass. Assuming you have, and this one applies to both ionizing and the particle radiation, as different from exclusion. Exclusion only applies to electromagnetic radiation, ionizing electromagnetic radiation. This one applies to both any radiation at all. Okay, even if we want to quantify the energy light, visible light imparts when it traverses a particular mass of tissue, and use this to quantify it, so on and so forth. So the energy imparted, assuming an energy of 20 kilogram, 20 joule. Talking about mass of maybe 0.2 kilogram. At the end of the day, we are going to have 200 over 2, which is 100 joule per kilogram. So this has to do with this helps us to quantify the energy, at least the ability, the destructive nature. The more the number of absorbed dose inside the tissue, the more the likelihood of damage to that tissue. If you have this 20 joule being supplied to maybe 20 kilogram of energy of tissue, the damage will be reduced by 10. Again, so we have 20 divided by 20 is kilogram, 20 joules. At the end of the day, we have 1 joule per kilogram. So for each a kilogram, the energy deposited is 1 gram. So this is a factor. This is a constant. This is a quantity that helps us to quantify the damage in a way, not holistically. But we're going to look at some other things that actually help us to quantify that. And one of such 10 is effective energy. The equivalent dose. Equivalent dose. So apart from absorbed dose, this is just for the symmetric it's for the symmetric reason. But if you want to look at the radiobiological want to look at the radiobiological significance of dose. We'll be talking about effective dose and equivalent dose. But let's start with equivalent dose. Equivalent dose, usually denoted by H, is simply absorbed dose. These are absorbed dose multiplied by a particular weighting factor, a particular constant, which we call radiation weighting factor. Because different radiation, they have different damaging effects. So you have electromagnetic array of the electromagnetic radiation of 2 mega electron volts. It is different from the damage that will be caused by alpha particle of 2 mega electron volts. This one is heavily charged. So as it traverses matter, it's going to cause so much damage. At times, irreparable damage than that which will be caused by this. So we have ICRP, they have come up to list the quality factor of different radiation. At least you have one for fast radiation. Neutron, they have their values Electrons have their values, usually 1, proton, usually 1, so on and so forth, alpha, and so on and so forth. And also depending on the energy of such equipment, such um, particles. For example, a neutron of maybe a speed close to the speed of light will have a much more damaging effect than a neutron, a slow neutron, which has um, a, a, a speed of maybe just 200 meters per second. So I want to quickly share with you because something on that radiation on equivalent dose on this radiation within factor. I hope we can say that. I hope we can see the screen I'm sharing.
Yes, sir, we can see.
Okay.
Yes, sir.
We can just see the radiation within factor for so many types of radiation. For X-ray, gamma ray, blah, 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 we have the radiation within factor being 1. 1 for proton, it is 2. Then neutrons, it is energy dependent at 2.5 to around 20. And thermal neutrons, they have close to 20, while slow neutrons have around 2.5, 10, and so on and so forth. Then for alpha particle and other multiple charge particle, they can have so many values, the maximum being around 20. So for us in a radiology, the absorbed dose and the effective dose usually the same thing because the radiation within factor is 1. And the unit of equivalent dose is also the unit of this. I will state, we should have stated unit of equivalent absorbed dose is joule per kilogram. Likewise, for equivalent dose, the unit is also joule per kilogram, but it has a special name. This one has a special name. The special name is gray. The special name for 1 joule per kilogram. So 1 gray, 1 GY, that's gray. Something as 1 joule per kilogram. Equivalent dose has a special name also. It has a special name. This joule per kilogram is somewhat different from this joule per kilogram because we're talking about the radiation weighting factor. You cannot apply the radiation weighting factor. Let's say the dose are absorbed is 20 joule per kilogram. Now absorb maybe 2. I'm looking at 40 joule per kilogram. This unit here, this quantity here has a special name. We call them sievert. Instead of 40 joule per kilogram, we just say 40 SB. So whenever somebody says this, the person will know that we are talking about a quantity that describes that has bring to bear the that has brought to bear radiobiology. It's different from this one, just a straight calculation. Apart from equivalent dose, we can also have the damaging effect on tissues. Damaging effects of tissues by different tissues, they respond to different damages. If you have a particular radiation, assuming you have a photon or you have an electron traversing a particular tissue, that's it, to the lens of the eyes, the damage is going to 1 joule per, maybe 1 gray. Damage 1 gray is going to cause to the eye. It's different from the damage it is going to cause to the skin. Skin can absorb maybe can accommodate maybe 10 gray or so, but the lens of the eyes, the gonads, they can't absorb that. They are very, very radiosensitive. So because of that, ICRP, International Commission on Radiological and Protection, also came forward to address that situation by a particular unit we call equivalent, an effective dose. Effective dose. Effective dose. So effective dose takes cognizance of the effect of radiation to different tissues in the body. So the commission came up with some factors. So effective dose is in the simplest form, can write E H multiplied by T. H as the effective dose, an equivalent dose multiplied by this factor, which we call the tissue protein factor, which is different for different tissue. So if we have a particular radiation built on the body, the total WT tissue weighting factor is going to be 1. And that one is usually subdivided based on the tissue. For example, I can have a tissue weighting factor of 0.3. The skin can have one of the 0.002. That's it. The weighting factor of skin is much less than that of eye. The gonads can have close to this, maybe 0.24. Maybe the bone, of course, if you have 0.000 whatever, much lower than. So at the end of the day, you are going to, if you calculate everything, all the organs of the body, it's going to give us 1. So when we are calculating effective dose, we just use maybe the effective dose to the eyes, effective dose to the skin, different from you are looking at a beta ray of 1 grade. Absorb dose of 1 grade. At the end of the day, effective dose will be different. For eye, you might have maybe 2 joule per kilogram. For this, you might have 0.8 joule per kilogram, and so on and so forth. This one also has a special name. It shares the same name with equivalent dose. Symbiote also has another special name. And we have, if I conclude this, also have some special units, some special names. REM, 100 REM, something as 1 symbiote, both for effective dose and equivalent dose. Whereas for absorbed dose, we have 100 RAM, equal to 1 grade. We can just read these things up, and then when solving the problems, I think they will get them cemented. Just trying to race against time because we've got to finish our quiz today. I think that's all there is about radiation units and interaction. If you have a few questions, I could use the remaining 35-40 minutes to go through the questions. Questions that's supposed to be a post topic test. Because of the timing, the time constraints that we have, I would have sent these things to after today, such that the post quiz will take place sometime maybe tomorrow, or because we are into the week of our second lecture, so we don't have enough time for that. So, but from our next lecture, maybe the next quiz might be sent maybe tomorrow, on Tuesday, as against our lecture, that is most likely going to come up on Wednesday. Then, before the last one, then after the last lecture, the quiz will be sent again, and now fix the time, which maybe 1 hour or so for us to come and go through the quiz questions. I invite all of us to Okay, you don't even have a quiz, except you saved it somehow. Let me see. Okay. Give me a minute. Okay, let me share the screen now. Let's have I hope you can see the quiz. Can we all see?
Yes, sir, we can see.
Okay. At the first question there, I don't think anybody should have any problem with that. Which radiation is not electromagnetic? Of course. That's ultrasound. Everybody should know that. The second one, X-ray, photon, and gamma always differ in their words. Is it energy, interaction with bone, interaction with muscle, or in their origin? Can someone just use the map quickly?
Origin, sir.
Okay, that's straight up origin. X-ray photons. X-ray photons usually, especially if we're talking about characteristic, now just from electron and transition. But for gamma ray, it originates in the nucleus. Isotopes have nuclei with what?
Same Z.
The same Z, straight away, straight up. For the number of neutron in cobalt 60 is just 60 minus 27. That gives us the answer straight. That should be around 33 or so. Number 5, the total number of nucleon particles is equal to what? Is equal to
D, sum of neutrons and protons.
Of course, straight up. 6. The binding energy of an electron indication is dash. Of course, this one is also straight up D. The energy required to remove electron from the K shell.
On the case, yeah.
The mass number, this one is also a giveaway question. The mass number is equal to the sum of the nucleons. The nucleons is proton plus neutron. Let's see 8. Electron binding energy. Okay, let's see 8. I think this is becoming much more interesting now. It's greater for K shell of barium than K shell of hydrogen. Why did you do that? Why did you go for B? I think we should be able to
Because
know.
Z is greater for barium than for hydrogen.
Why is it greater? How?
The Z now, like the, what do you call that?
Yeah. It's greater
Atomic
for
number.
Z is greater. Yeah.
The atomic number.
The atomic number is great.
The higher atomic number.
Okay. Well, it's okay, but it's actually because of the nuclear whatever. Well, it's okay. The excuse you have given, the thing you have given is valid up to an extent, but at times it's no longer straightforward. But so anyway, it's greater for K shell of barium than K shell of hydrogen. Hydrogen doesn't have so much nuclear material, just but for Z, for barium, it has so much, and because of that, you are going to have so much more Coulombic attraction and the nuclear whatever, nuclear disease. So we're going to make the attraction between the K shell, the electrons, and then the positively charged nucleus becoming much more. The atomic orbit closest to the nucleus, this one is also a giveaway in Askisha. And nucleus with the same A and the same Z, of course, and this one is also a giveaway. With the same A and different Z are called what?
Isobars.
Okay. Cobalts 57 and 58 have the same number of what? Cobalt.
Orbital electrons.
Electrons.
Chemical.
Yeah.
Electrons.
Yeah, orbital electrons. Of course.
Okay.
Sorry. So which of the following is not true regarding electron binding energy?
Is not true.
Which is not true? This question, they are also straightforward. It's not a true false question. Maybe some other time we just look at few true false questions. Which of the following is not true?
A. Yeah.
A is equal to the energy of the characteristic, of course, which is very, very untrue. That's very, very untrue. A is the characteristic S-ray are so named because they are characterized by
B. What is it?
electron binding energies of the atom. Of course, electron binding energy of the atom.
Okay.
Which is a unique to every atom. So let's look at something much more interesting now. 14. Something has the following binding energy and indicated in the table below. In order to observe 57 electron volt characteristics, the Israel electron will have at least an energy of
70. B.
Okay, how did they come about that?
B higher than the 69.
Okay. But actually, the least energy has got to do with the transition from '69. Of course, just 70. There shouldn't be. If you have an energy of if 157, the difference between this K and shell is actually 57. So for us to be able to detach this electron, this one has to be detached so that K electron, the L electrons will fall into K. For that to happen, you must have at least 69 electron volts. I mean, kilo electron volts. And if you don't have up to that, we are not going to have any K characteristic X-ray. So it's 70. Which of the following is true for polychromatic S-ray beam? Okay. Which?
Second age ray is greater.
Yeah.
Greater than first. B.
Yeah. B.
B.
The number of competing electron and tissue is equal at which temperature, at which energy? Let me see. This is I didn't. This question is not too clear anyway. Give the answer as 25, but I don't think so. I think it's closer to 50 something kilo electron volts. We have the graph. Can we see the ball?
Yes.
We have the computing. And then the part of intersection between this continent is around 50 kilo electron volts. I think it's but anyway, we can just go and do more research on that. But it's not. I don't think it's exactly 25 kilo electron volts. Anyway, let's move to other interesting questions. 17. The mass electric blah 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 is approximately 4. What will be the distance at 10 centimeter square per gram? Attenuation coefficient, and that's the mass attenuation coefficient. So at 120 keV, it will approximately be what?
Or
40. Okay.
See.
I hope I have told you to use the whiteboard there to do that, but that might solve it. That might waste some time. Might give you the permission to use to screen share your whiteboard. But it just this, you know, and you can see the board. No, put electric emission coefficient is inversely proportional to energy. Energy Q. So if you have can have P is equal to, let's just introduce a constant, and use carefully constant. So we have K, the constant is let me use the mass coefficient for electric emission, PE. Let me use that. So this are you here. So this is a constant. So this implies that if we have E1 it should be equal to another value at another energy, another value, another energy, and so on and so forth. So this
So we're not seeing the board.
Okay. Okay. Let me use a black marker. Let me put are you seeing now?
So the board is not projected. It's the questions that we're seeing.
Okay, let me stop. Let me stop this. How do I always go back to the question. So you have a mass electric emission coefficient U is directly proportional to energy raised to power 3. That is for electric effect. For Compton effect, is just simply 1/E. So if you have at a particular energy, okay, U is simply if you introduce the proportionality constant, a particular constant, whatever it is, U raised to power 3. So this can this constant U raised to power 3. And put one here, the same thing as E2 the same thing as another set of energy and coefficient. So U4 E over raised to power 3. So at a particular energy, you have E, it's the corresponding at the mass attenuation coefficient. It's going to be the same thing when you change the energy. When you change the energy, you are going to have another value. You change the energy to another value, then you have another value. So for our question, I think, let me see this question. Our question is 12, 4, we're looking at 120. Okay, 120 down. Oh, okay. Okay. So we start at 4, I think 12 kilo electron volts. It was 4 centimeters squared per gram. You should find the mass attenuation coefficient at 120 kiloelectron volt. So you can take this one. This one first energy, post what's it? The value at this energy. Then at this energy, this second energy, we should have another value of mass attenuation coefficient. So we have the first energy, the first mass attenuation coefficient being 4, multiplied by the energy being 12 raised to the power 3 equal to what we are looking for, multiplied by 120 raised to the power 3. You can simply have this 4 times 12 equals, you don't really need them. Times, this is 10 times 12. 10 times 12. So we have 12 raised to the power 3 times 10 raised to the power 3. So we have this out. So when you we now have 4 over 10 raised to the power 3. That's 4 over 1,000. That's 0.004. So we have a 0. What's it called? 1.7. Let me share the screen again. Oh. Okay. So we're going to have a 0.004 centimeters squared per gram. So for the next question, Compton interaction does what? Increases with increasing energy. Interactions increase, so which is the best option here? Compton interaction, ABCD. What is it? Ask.
Yeah, increases with increasing energy. A.
Increases with increasing energy. A is wrong. It actually decreases with increasing energy.
Is B. Change the direction.
Yeah, it changes the direction of the incident. Changes the direction. Interactions change the direction of the incident photon at times, but not always. But most times it changes the direction of the incident and photon. At times you can have the direction still the same way, 0 degrees difference. So it is actually it doesn't increase the contrast in radiograph. It actually does the same, the opposite, reduces the contrast. They are more important at low S-ray energies. For low S-ray energies, photoelectric emission is much more important. So for 19, so this is B. So for 19, the difference in X-ray attenuation of bone as compared to muscle is bone has a higher atomic number. So what is the person? What's the best option here? Okay.
B.
It should be bone has a higher atomic number than tissue, and 3, bone has a higher mass density than tissue. This is wrong. 2 is wrong. Bone is less resilient than tissue. Very wrong. Bone has a higher snap coefficient than tissue because refraction, in get to refraction, we know that is also very wrong. In fact, since we don't have 1, 3, and 5, if we had have 1, 3, and 5, we might in battling with these snares and coefficients. But since we don't have 5, it makes the work easier. So 1 and 3, so 20. If a particular calculation of, I think we've solved a question like this before, so we shouldn't have a problem with this. Number 20, we solved a similar question. So using the method, and equally solve this one also. This is straightforward. 21 is diagnostic energy range. When the atomic number of an absorber changes from 20 to 40, what happens to the mass attenuation coefficient of material 2? Is it going to be more than that of 1 or less than what? Same thing. Or let's answer the question based on the limited number of parameters we be given. Just because of time.
I think it should be greater.
A, greater than.
I think it should be greater.
Yeah, it is going to be definitely greater than, because linear mass attenuation coefficient is directly proportional to the linear attenuation coefficient, and the linear attenuation coefficient is directly proportional to the density of the material. So when the density of the material changes, as Z changes, of course, the density of the material changes. So it's going to have much more attenuation than the one in which Z is is 20. So for 22, for 20, number of protons per gram for going to happen. So what's going to happen? From Z to 20, Z20 to Z40, what should be the number of photons per gram absorbed by the photoelectric effect in material? One is related to 2.
Zero point 0.5.
0.5. So if you look at 20 over 40, that gives us 2. So our answer should either be 1 over 2 raised to power 3 or 2 raised to power 3. Because we are talking about the photoelectric effect, it is directly proportional to Z. It is directly proportional to Z. Maybe I should use the board again for this question. Let me use the board again. The photoelectric effect coefficient is since photoelectric effect is directly proportional to Z over E. So it means PE is proportional to photoelectric coefficient. So we now have introduce a constant. Okay, we are looking at this one. We are not looking at energy now. We are looking at the Z component only. So we can have this really important to introduce a constant here to do away with this. So we have K now. K will now be this over Z. So for different values of Z, we have let's say U1, U2, Z2, 3, U3, Z3, U4, Z4, and so on and so forth. So for the first one, the Z was 40, the Z was 20, or 3. For U1 or the U2 was 40, So if we want, they said ui over, so mu1 over mu2 is simply 20. Sorry. So we're looking at mu2 over mu1, which is 40 cube over 20 cube. At the end of the day, we are going to have 2 raised to power 3. It's going to give us 8. 2 raised to power 3 is going to give us 8. So right from the word go, if it has to be because 20 over 40 or 40 over 20 as the case may be. Since we weren't, we don't have a 1 over 2 raised to power 3, which is 1 over 8, and there is 0.125. You don't have that yet. I don't think you have any problem. So the let me continue with sharing. So the number of photons per gram of the photoelectric effect in material 1 is 8 times as many relative to that of the material 2. Okay, I think we are within time. 23. 70%, 75% chance a photon in a monogenetic beam will be attenuated by 2 millimeters of length. What's the HVL? Becoming interesting. Any ideas to how to solve this? You need to claim what you want to get. Then look at this question. I'm sorry, I've got to be as fast as possible. And 70% chance. It says 75% chance. And 70% chance, and the thickness is 2 millimeter. So we should find the HVL. HVL is what? Okay. Let me stop this share now. We said we have 75% chance. Chance of what? Okay, chance of attenuation. Okay. Okay, photon beam has a 75% chance of attenuation. Let's say monoenergetic beam. Okay, whatever. This is the equation we use, n naught epsilon minus mu s. Because this is the much more general equation. It's not the same thing as this, and you can't use this because we weren't told that this 2 millimeter lead is a small thickness. If you have been told that, you could have used this one straight up and not under S. Mu under S. We have used this one straight up. But since we weren't told that, we got to use the much more general equation. 75% chance of being attenuated. But mind us, this n is the amount of photon transmitted. Whereas we are given that 75% chance of being attenuated. So it means this 75% of whatever being attenuated is the n we are talking about here. It's different from this n. This n is actually the number that was transmitted. So if 75% chance was 75 was attenuated, it means 25% was is actually the number that was transmitted. That is this n over n naught, which is epsilon minus lambda x. This are n over n naught is the 75% that was attenuated. I mean, n over n naught will now be at 25%. This n over n here is the 75% attenuation, but this is the number that was transmitted. It means that just 25% was transmitted. So we have 0.25, which is at 25%. 25% is simply 0.25. So 0.25 is epsilon e x. So if we, I think if we take the natural logarithm of this side, I have calculator here. Can somebody get us the natural logarithm of 0.25? Just press your calculator, lane 0.25. Let's see what it's going to give us. Just press lane 0.25. And use your phone. And just about 7 more minutes to go, thereabouts.
Please, I don't understand how you got 25%.
Okay, I said n over n naught. This n here is the number of transmitted photon, transmitted X-ray. But we were told in the question that 75% of the X-ray or photon was attenuated. So it means 75 was removed. Remaining 25. So n over n naught will now be at 25%, which is 25 over 100, 0.25.
Okay. Okay.
So can someone get us the lane E of this natural logarithm?
Minus 1.39.
Minus 1.39. Okay, minus 1.39 is simply, we have looked at the natural logarithm of this. If we get the natural logarithm of this, it's going to give us minus mu x. That's a little small mathematics there, but it shouldn't. Let's not forget that we all learn these sciences in school. So we have blah blah blah. So mu x mu. Our x is 2 millimeters. Okay, let me see, which is minus mu times 2. So mu will not be minus 1.39 over 2. Whatever that gives us, of course, negative, they are going to cancel out. At the end of the day, whatever that, let me quickly use my own calculator. And somebody should give us this. What's it? What's the value?
0.695.
0.61615. Okay.
6995.
Okay, 695. 0.695. So what we know that our HVL, HVL is 0.693 over this. So HVL is simply 0.693 over 0.695, which is approximately equal to 1. 0.99. Yeah, very close. So that should be 1. Let me continue with this here. So that's essentially 1 millimeter. Compton scattering involves, I think, so we can say of Compton scattering involves scattering from outer shell electrons. That should be big.
Yeah.
You don't have any problem with that. 26.5. Photoelectric absorption involves complete absorption of the incident photon. It absorbs it completely. With that, I don't think we should look at any other question, any other option. This is identify the following portions of the core video for question 26 to 29. Please supply your answer in capital letter A, B, or C, or D. So for this curve A is the total portion. In fact, this is the photoelectric. B is a photoelectric. It's a straight line curve. This one here is for a Compton scattering. C is a Compton scattering. You see, whereas this one is straight, because the pair production. You can see the energy range. This 1 megaelectron volts. That's 1,000 kiloelectron volts. So for this one to occur, the energy must be more than 1.02. So that is that about that. If the display intensity of
Sorry,
image,
sir. Excuse me, sir.
okay, so go back.
Curve A is what, sir?
You said?
Curve A. What is curve A?
Curve A is the combination of all these curves. That is, if at this point you have a particular number for this and you have a particular number for this, maybe 2 and then 3. At the end of the day, you plot, you put the point here. For this one, you have maybe 2 and 2. You plot it here, and so on. At this portion, this one is no longer existent. The whole thing will not depend on the Compton scattering. We now continue until we get to this place again. We now begin to add up the effect of Compton, and at the end of the day, you can see when Compton is no longer existent. So from 1,000, 1.02 electron volts, all this one, they are still there. The graph is not, this is not a comprehensive graph anyway. So A is the combined contributions of all these mass attenuation coefficients. So in the display, if the display intensity of the image is maintained at the same, the image obtained with higher KVP is expected. And this we're going to talk more about when we get to our next topic. But essentially, with higher KVP, we have a lower contrast. So it is lower KVP that gives us the best contrast, good contrast. Question 31, I think. Question 31. 31. In the linear attenuation, they have value layer. This one is also straight up. We use the same equation we used before. Here, linear port to 0.693 linear attenuation coefficient. So if the mass attenuation coefficient of a material is this and the density is this, what is the linear attenuation coefficient? We know the relationship between linear attenuation coefficient and mass attenuation coefficient. Mass attenuation coefficient is linear attenuation coefficient divided by density. So we just put him in there. What's the linear? Okay, yeah. Okay. Now you multiply. What's the linear attenuation coefficient? To get the linear attenuation coefficient, you multiply the mass attenuation coefficient by the density. Since mass attenuation coefficient is linear divided by density. So linear is mass attenuation coefficient multiplied by density. Okay. We've treated this question before. 33. Repetition. So what are the products of a coherent photon interaction? What are the products?
It's scattered photon.
Yeah, scattered photon. This is actually the Rayleigh scattering. When they have a scattered photon, nothing else. No electron is ejected. And of course, no photon, no positron. What interaction is responsible for image contrast? Of course,
Photoelectric.
what interaction requires at least 1 point? Of course, we all know that.
Here.
The interaction varies as 1 all over e raised to power 3.
Photoelectric.
Yeah, I didn't complete the statement. I wanted to say E3 is red, e raised to power. Okay, that's about that. The interaction is more likely to occur for a 90 kVp X-ray beam incident on tissue.
Photoelectric.
That's photoelectric. Just
Photoelectric.
No, I think he's counting something.
yeah. Answer says photoelectric, but that's not correct. It's actually Compton. It's a Compton scattering. For higher energy, photoelectric is from 50 kiloelectron volt down. But when the energy begins to move further than that, the major contribution is from Compton. So this one is answer is a Compton scattering, not photoelectric interaction. So this is that for this topic. We need to send some people requested for some slides, which I'll try and lay my hands on and send. Oh, I don't know if you have any questions, you could chat me up. You can ask the question on the groups and page, or send a message directly to me. It will even be better for us to share it on the groups page. So if you have any other question right now, you can ask. As we see how it goes. Before I'd like us to finish the next topic, of course, based on the timetable. I have another lecture on Wednesday, and after that, for the next topic, the lecture should be on Wednesday. Then during the lecture, at the end of the lecture, we will now sit down to plan to see when the next one will come up. So our next lecture will be on Wednesday. And before that time, I would like us to bring our inputs as to which time will be convenient for all of us. So I feel this time is very convenient for so many of us. So, you have questions? If not, we might have to call it a day.
Thank you very much.
Okay. I think we don't have questions to ask. So before our next lecture, I'll also send those of us who haven't submitted, those of us in the group who haven't submitted an email, we just do that by sending it, so that the next line of questions, the next question for the next topic will be given us before we start the topic at all. So just send me your email. Send it directly to me, or just put it on the group page. So I want to thank all of us for joining. And sorry, Dr. David.
Sorry, sir, I didn't hear what
You didn't hear?
you said.
Okay, you didn't hear what I just said. I said, I think I seen it, the email address of a few more people.
Your last statement.
It's about the email address. I said I'm going to send a quiz to
Email, okay.
email
Okay,
boxes.
yes.
The pretext for the next topic has to be sent to your email boxes, and you just give me the response before we start the lecture on Wednesday. So if you haven't submitted your email, for those of us registered in the group space, just try and do so.
Okay.
Once again, I
Sure.
want to thank us all for active participation. Signing off. Bye-bye.
Bye. Thank you, sir.
Hi, sir. Thank you.
Yeah, bye-bye.